So welcome back to VLSI lab. So today we'll be covering the second half of layout. Okay, so we started off with inverter layout. We made a layout. Now it's time to do something called Assura. The tool itself is named as Assura, and it is a part of your layout schematic only. You don't have to invoke any other separate tool. It is inbuilt for layout. So this is the second half of layout, wherein you have already completed the design. That means the layout of your experiment, you have already designed it. Then now it is time for some checks. Okay, you have to test it and verify it that whether this layout is correct or not. Okay, so 3 tests will be done. One by one we will see what are they, and all these tests will be done via Assura. Assura, not the web series present in Woot. Okay, so now let's start off. So my library is selected. From my library I selected the file wherein my layout is present. Okay, so it will be inverter. I can see layout, so I have clicked on it single time, so that's why it's highlighted. So now I'll double click on it. Okay, so this is the layout schematic window. I'll maximize this window because it's of use for me. Now in our last session we saw that the source, body and drain terminal were visible. Now it's not. Nothing to panic, they didn't vanish away, they are just layered inside. So how to access that? Simply press Shift F and you'll be able to see them. Okay, see, understood? So now this is our layout. So our layout was complete. According to the schematic, my layout was designed. Okay, now in our last session, one of the question in the quiz was asked that why should layout match the schematic, or like this layout, PMOS is on top, NMOS is at the bottom, input on the left, output on the right, VDD on top, ground on at the bottom, and body terminals are integrated with their respective source terminals. So the question is why? Okay, the question why. Chapter 3 of VLSI, I think module 2, you learned something about design rules, right? Over there you must have studied that the layout must follow schematic. Okay, the reason of that is when we are sending the designs for fabrication, the chips, okay, the 5G chip being designed by Qualcomm 865, right? So that's a chip, isn't it? That processor is a chip. So let's suppose you designed it via some tool and you want it to be fabricated. Okay, or just remember any ICs that you have come across so far, like in your LD lab, some ICs you were using, right, for all the logic gates, isn't it? So that black color thing and some pins coming out of it looking like spiders, right? So that was fabricated. So how will it be fabricated? So the design has to be sent to the foundry people, wherein they will fabricate your design. Now when you're sending the design to your foundry, you're not going to send the schematic or the test circuit. That is of no use to them. They don't bother themselves with that. What they want is the GDSII format that is generated from the layout. That they want, nothing else than that. Now that is why, since the GDSII format that is required to fabricate your ICs is generated from the layout, hence your layout should match the schematic. Okay, so instead of sending the schematic, you're sending a format that is generated from the layout. Okay, and that, since you're sending that, not the actual schematic, not the actual circuit, that is why layout should always match your schematic. No disparity allowed. Okay, so that is the reason why. And yes, it should always match. So I hope some of your doubts are cleared. Now, so this is my layout schematic, right? So I can see all the tabs on the top. third from the last, okay, is named as Assura. So this is our tool. Click on it once, okay. You see there will be a list of drop down options. Now third option from Assura, technology, okay. Click on it. You will get this rectangular window. Now something is written over here. This is the path, Assura technology file. Assura needs to know what you are trying to do, which technology you are trying to attach. So which technology we have attached? GPDK 180, and the type of experiment going on is analog, right? So we need to give a path, a technology path to Assura, so that Assura understands, okay, this is what they are up to, let me try and fix it, okay. So this, because I have been using this, that's why the path is already there, but for you need to write it down, like you have to set up that path. So one by one we will see the path, so you need to note down what comes after what, okay. This is important. You make a mistake in this path, nothing will be done beyond it, okay. Now beside this path, can you see this 3 dotted option? 3 dots, can you see this part? 3 dots, whenever you see, that means browse, okay. If it is a 2 dot, it means reverse path, okay, going back, it means that, okay. Remember these things. So click on this browse, okay. Now see, I have got a single dot and a double dot on the left column, so I need to go back, okay. So I'll double click on it quickly, okay. See, it's going back. Now from here, see, nothing else is there, so this is my starting point. So from here I'll find out home, okay. Now double click on it quickly. You do not have the chance to wait for it. From home you have to click on CAD, okay, not Cadence. You have to click on CAD, double click on it, okay. After you have clicked on CAD, you have to find out Foundry. You have to find out Foundry and double click on it, okay. From Foundry you have to click on Analog, okay. Now which technology file you had attached? GPDK 180. So you will be clicking on 180 NM, okay. Double clicked on it. Then from there, till now we were on the left column. Now we will go to the right side column. From the right side column, after 180 nanometer, I can see a name, Assura_tech.lib. So I need to double click on that, okay. So this is my path. I'll click on apply and click on OK. So my technology path is added. Now again I'll go to Assura and I can see one option called run DRC. I can see the option run DRC. What is DRC? Again, module 2 chapter 3 VLSI. The thing, this DRC is nothing but design rule check. So what you studied in chapter 3 were the design rules, and your layout should follow these design rules, okay. Layout should follow these design rules, okay. If your layout is not following that those design rules, then there will be a violation, means errors will be there, okay. So if errors are going to come, that means you have to go back to your layout and rectify those errors. You cannot have any other option apart from validating the DRC, okay. So in one of the questions in the quiz was asked that how many errors were discussed. So one of the errors discussed was the mismatch error. Remember the gate terminal that we were going to connect from PMOS to NMOS, and at the NMOS side there was a slight mismatch, right? And then we dragged NMOS to remove that mismatch, right? So there was a perfect connection. So what will happen if that connection I didn't rectify at that time? It will give me a DRC violation. It will give me a DRC violation. Okay. Then again, what else was there? Body terminal not present, then that will give me a design rule error, and it will also give me another error that we will see next after DRC. Okay. Then if you do not connect a via, okay, so that will also be a DRC. What other errors will be there under DRC will be that the PMOS and NMOS are too closely placed. Overlapping error will be there. So all those things will be there. Okay. So these things were already discussed while you were learning your VLSI. Okay. So I'll just click on Run DRC. Okay. So I'll get this window. A big window I'll get. Run Assura DRC. Okay. Now from here nothing you have to change. The only thing you have to take care is that this middle drop down. Okay. So when you are starting on your own for the first time, okay, so what you will get undefined. So what do you have to do is click on the drop down and select GPDK 180. Understood? Since I am repeatedly using the tool, for me it is fixed, but when you will come, you will create your own library and do the experiments. At that time you will get that undefined problem. Okay. If you don't change that drop down, you won't get results. So you have to click on the drop down and select GPDK 180. These are all the steps that I'm discussing. I hope you people are making a note of it. Okay. So click on apply because I made a change, and then click on OK. So it is simulating. Okay. And see, this is the progress tab that I'll be getting. Okay. So if you want to see what all is happening, you can click on the watch log file before it stops. Okay. So just read what is written over here. The DRC run inverter from this has completed successfully. Do you want to view the results of this run? Yes, I would like to view the results. So this is what I need. No DRC errors found. This is the aim. Okay. Now let us see what will be the errors. How if I get some errors, how will it look like? Okay, in the results, DRC results. So what I will do is I will simply go down. Okay, just a moment. And I will select the NMOS and I will create this mismatch error. Okay, let's suppose this is it. So again, if I am making some changes, it will be Shift X. So now what we will do is, again we will do the DRC run. We will see how it comes out. Okay. It takes some moments. Okay. Click on, this is your log file. Alright. That the DRC is working out. So DRC run is over. I would like to see the issues. Now see, this is your error window. Okay, see, what does it say? This side is your error. This poly width must be greater than equals to 0.18 micrometer. Okay, so now I'll click on it and then I'll click on this arrow. I'll just close this and I will minimize this error window. See, this tool is indicating where the error is. Okay, so So what we will do, we have to rectify this error. So we know how to do it. So we'll just drag the NMOS and place it. Okay. So this is how you. Okay. So we will just save it. Again we will run DRC. So every time you are doing, you have to get that no error. It shouldn't be like okay, I rectified it, so I don't need to check it again. No, you have to get that no error, no DRC error thing, and you have to take a screenshot, and all those things has to be done. Okay, now we will view and we will see no DRC errors found. Okay, so that is how you will see the error from that particular window and how to rectify. Click on the error, click on the right side arrow, and you will get back to the layout window. From there you have to rectify the error and save it and run DRC again. Okay, so this is how you get the error and rectify it. Clear? So DRC run is done. So our layout validates the design rules. That was the goal. Again Assura, and after that we can see run LVS. What is LVS? LVS full form is layout versus schematic. So what is the goal of this test? That it will check whether your layout matches your schematic or not. Okay, it matches your schematic or not. Okay, so that is what we're going to see. Click on LVS. Again you will get this part as undefined, so you need to click on it and make it GPDK 180. You don't need to change anything else from there. Now click on apply and click on OK. So again you will get a watch log file for the LVS also. Okay, if you want to see, you can see that. Okay, now see over here, let us read what we have got. Summary of LVS issues. Okay, 0 cells have 0 malformed device problems, 0 cells have 0 label short problems, 0 open problems. That means there are no shorting of wires, there are no open terminals, and the devices are not malformed. There are no net mismatches, means the wire that is connecting two devices in your schematic is present in your layout also. The way that means the way you have interconnected your devices in the schematic matches that of the layout. Therefore no net mismatches. No device mismatches, of course, PMOS on top, NMOS at the bottom. No pin mismatches also. Input is connected to clubbed gate, output is connected to clubbed drain, VDD to VDD, VDD to source and body of PMOS, and ground to source and body of NMOS. So pin mismatches are also not there. Parameter mismatches is also not there. Okay, so this is via which we know there are no LVS issues. Okay, that now see, you will get, after you have clicked on that, you will see another window pop up which says schematic and layout match. So this is the window, that is the aim. So if you guys would have been over here, you would have taken a screenshot of this and stuck in a lab record as a proof that yes, your LVS run was successful. Okay, so done. I'm done with that. So I'm done with LVS also. Next is what? We will go with run QRC. Run QRC. So from this QRC, what are we going to do? We are going to find out the parasitics. Remember the parasitic capacitance, parasitic resistance, which take up a lot of power and they add up to the power dissipation and power consumption of our devices, which is bad, right? So as a designer, I would need to know how many such parasitics are present in my design, right? So that I can say that this device will consume this much. Okay, so that is why we have to come over QRC. So from extraction, okay, the type we have to do is both I want to find both parasitic resistances and capacitances. So I will click on RC. Okay, I will click on RC. Alright, and make a note, after clicking on RC, extraction type drop down, you have to click on RC, and can you see this last option, ref node? That is nothing but a reference node. So you have to type GND and followed by one exclamatory mark, no space in between. Okay, so that is what you will do. Otherwise, if you just simply write GND, you will get some errors, you will not get the proper output. Okay, so you have to do that. Then yeah, I guess that's about it. So I'll click on apply. I'll click on apply, click on OK. For this also you will get a log file, so you can watch it. So after this QRC has been run, you will get something called this pop-up will tell you that the QRC run inverter completed successfully, and the output is in this location. What is the location? Library, your library, cell, your cell, the name that you have given, and the view is AV_extracted. Okay, so that means whatever result this QRC is given to you, it is not in this layout, it is somewhere else. So let us go and find it out. Okay, so I'll click on close, and I'll close this log file also, not required. So I'll go to my library file. Now see, earlier on we had only 3 files inside of our inverter: layout, schematic, symbol. Now I've got a 4th one. What does it say? It is AV extracted, right? So let us double click on it. See, it is another copy of your layout itself. Now what we will do is we will zoom in. Okay, can you see this red rectangles over here present inside your layout? What does this say? P capacitor. And if you come on this side, what does it say? P resistor. What does this P capacitor and P resistor means? Parasitic capacitance, parasitic resistance. So I want to know what's their value. So what I'll do Shift F. Okay, see, now the symbols have come. This capacitor, resistor symbol. So I'll zoom in on this capacitor now. Can you see the value is written as C equals to 76.9593 A. What is small a represent over here? What is the unit of capacitance? Farads, right? So now what is it writing? A. A means atto. Okay, A means atto, ATTO. So femto is 10 to the power of minus 15. What is atto? 10 to the power of minus 18. So your parasitic capacitance over here, the value is 76.9593 into 10 to the power of minus 18 farads. Okay, so if I just go towards the resistor, what do I see? 1.523 ohms. Okay, likewise I will have several such parasitic capacitance and resistance. Just see over here, this is my parasitic resistance. Some value you are getting, the value is not clear over here. I'll tell you what the value is. It is 29.0198 ohms. Okay, now see one good thing. this is a parasitic MOSFET. You remember chapter 2 module 1, wherein we studied something called the bi-CMOS technology. So it was a combination of BJT and CMOS, wherein you were not connecting the BJT separately or externally. It was present inside the MOSFET as a parasitic. So likewise, this is a MOSFET present as a parasitic inside of our design. Okay, how is a MOSFET formed inside a MOSFET? Think on that. Okay, another resistor, parasitic resistor I can see. So if I go on this side, what do I find? I find another resistor. So likewise, I think you're getting the hang of it, that all over the design we will be finding several parasitic components. Okay, several parasitic components are found. So from where do we get this parasitic information? From the AV extracted file, not the layout. Okay, so this is the complete flow of your layout. So in our next session, we will be looking inside the layouts of common drain and common source. So this will be all from for today. I hope you have understood. If any doubts, you know how to contact me. That will be all. Let's wrap this up. Thank you.